Hi everyone, this is Ezekiel O'Callahan with Raptor Chatter, and we're going to be looking at what happened in August 2022 in paleontology. So let's get started. For vertebrates, or animals with a backbone, breathing air was an entirely new adaptation in the Devonian, when animals like Tiktaalik actually started to move onto land. But there's been some questions about how did they actually develop this capability. And this study actually looked at lungfish, so the closest living relatives to things like Tiktaalik. But there's been some question as to how these fishopods, because they're kind of more like fish and not quite tetrapods, how these animals actually started to breathe air. In order to understand this, the researchers x-rayed modern-day lungfish. The lungfish are actually sister group to tetrapods, so they might actually provide a really good example of what the breathing apparatus in things like Tiktaalik may have actually been. And what they found is actually there wouldn't have needed to have been a lot of changes to the morphology and the bones in these early fish moving to land, at least not as much as we would have thought. And that's because many of these lungfish already use what's called suction feeding, and you can actually see it in this video, where essentially the bones in the parts of the head and nearby the head expand backwards, opening up a lot of space in the mouth. And then from there, the water gets sucked in and the prey as well. Meanwhile, what they also did is they tested what these fish would do when they were breathing air, also using x-rays, and you can see that in this video, where the same mechanism acts to suck in the air, and then that gets directed to the swim bladder, which later evolved into the lungs. So it actually makes a lot of sense for how these kind of animals were actually able to start moving to land and breathing air. There wasn't a lot of complication to it because they already had these mechanisms in place. And staying with the theme of fish, we're actually going to be looking at one of the largest fish to have ever lived, and that's megalodon, or at least the species megalodon, or Otodus megalodon, as opposed to the genus megalodon, which was a kind of clam. So what we're looking at actually is how big megalodon, the fish, could have actually gotten. And these researchers tested this by scanning multiple vertebrae as well as some teeth. And from this they were able to build up a composite of how big megalodon could have gotten. From the data gotten from these CT scans, the researchers estimated a length of about 15.9 meters, or around 52 feet. And from this they were also able to try and test a few other ideas. First of all, like how large its stomach volume would have been, and then potentially also what its cruising speed would have been. So not maximum swimming as fast as it can speed, but how fast it could have traveled from place to place. And this is actually really interesting because all of these come together to help us understand better what its specific niche would have actually been in the ancient oceans. First, because of its larger size, they actually found that it would have had a faster cruising speed than most other sharks, being about 1.3 meters per second. This means it could have actually traveled pretty long distances pretty regularly. Then they also looked at what potential prey items would have been in the water and how large its stomach could have potentially been. And in this graph you can see where they actually plot these two things, how large the prey item was and how often it would have needed to feed, with larger prey items obviously needing less regular feeding, and smaller prey items meaning it would have needed to feed more regularly. They came up with these numbers by comparing the measurements they had taken and comparing them to many modern-day sharks that are related, specifically in the group of the lamniforms. So this is things like the great white shark, but also makos, and one of my favorite sharks, the porbeagle shark, because it looks kind of cute and goofy. Unfortunately for megalodon, it did still go extinct because it wasn't living exactly the same kind of lifestyle as a shortfin mako or as a porbeagle shark. It instead was living like a megalodon, and only by combining all of these models can we really try and narrow down what it may have been living like. And again, it didn't work out for it, which is unfortunate, but hopefully this paper starts laying down some of that groundwork so we can better understand why it went extinct. Staying in the water, there is also a new fossil species of mosasaur found coming from the very latest Cretaceous of Morocco. And there's already been some debate, at least on Twitter and some public spheres, about whether or not this animal actually does make up a new genus. And that's because it's been named Thalassotitan atrox. And the thing is, it actually places itself really nicely within a broader genus group known as Prognathodon, which means some people are saying no, it should actually be Prognathodon atrox, because it is a new species based on what they found in the bone. So what this really comes down to is some differences in taxonomy, where some people are going to say things like, no, actually, this should be Thalassotitan and not Prognathodon, but also Prognathodon needs to be broken up into even more species. Meanwhile, there are people who are lumpers, where they go, no, we're going to lump all of these together, they are Prognathodon, even if they are different species. And the mosasaurs were lizards, and that brings us to some lizards that are actually really close to home because some of them still live near where I live. And these are the teid or whiptail lizards. And this one actually genetically sequenced the different lineages that do exist in parts of the southwestern United States and parts of Mexico. And what they found is there's a lot going on. So you can see here that there's a lot of species that they sampled, but also a lot of times different species interbreed with one another, and there's a lot of different things that this has caused. For example, the red lines means that there would be a hybrid of two lineages, and then the hybrids would be breeding with both parent species for a while before becoming a more distinct species. The blue lines mean they evolved parthenogenesis, meaning there's no males in these populations. And then the purple lines mean the same thing with the parthenogenesis, but that they're triploid. All that triploid means is that it has an additional set of chromosomes. This is actually really commonly seen in some types of plants, where normally they'll be diploid and have just two sets of chromosomes. But then sometimes you get them that have more sets of those chromosomes, and that means the fruit in general gets bigger. So that's why you see some wild strawberries that are a lot smaller than some modern day strawberries, is because we've selectively chosen the ones with more chromosomes because you get more fruit for your same plant. Now, in the lizards, that doesn't actually mean the lizard itself is larger, because in animals, generally those extra sets of chromosomes are turned off if they do show up. So they're normally not too big of a deal for the overall health of the organism, and it does develop just as it normally would under normal conditions. The thing is, when you look at some of these lizards, like Aspidicellus neomexicanus, it's also really similar to one of those parent species, which is Aspidicellus arizonae. And these are both just separated partially by region, because the New Mexico whiptail, Neomexicanus, isn't as common in Arizona and vice versa, but also Neomexicanus has a wavy line down the back instead of a straight line. And in some cases, those are the kinds of differences that we're actually looking at. And it really goes to show that evolution can take unexpected pathways with hybridization, but also that species are really, really hard to try and define sometimes. And maybe we need to reconsider how we do teach some of these species concepts in the future. And staying with things like DNA, we can actually do eDNA, which is where you sample something like soil or water and separate out the different types of DNA from things like shed skin follicles that actually do exist in those two different substrates. And from there, you're able to separate those out and find out what was living in that ecosystem or what is currently living in the ecosystem. The thing is, if we're doing this in the fossil record, it means there needs to be really good preservation. And one place that can happen is in many types of permafrost that occur in the northern hemisphere. For example, in Siberia. Unfortunately, a lot of the permafrost is melting, which means there are large slumps, or essentially landslides, that are occurring in some parts of the tundra. However, that also means that some of those sediments that get exposed can be tested for eDNA. And that's what these researchers did. By testing in multiple spots, they were able to identify different ecosystems and communities that existed at different times, most notably when the glaciers were further south or when they pushed back north. And there were a number of interesting findings. There's a lot of the expected things like mammoths, a few predators, and really unexpectedly, ground sloths, which is something we absolutely didn't expect from this. In general, ground sloths come only from the Western Hemisphere, or the Americas. So finding DNA of a ground sloth all the way into parts of Asia is really odd, and hopefully we'll find some more fossils of this kind of animal so we can actually understand how they may have been different from the parent populations which came from South America. And with a lot of these animals, they're extinct now, meaning their place in the ecosystem has changed drastically because they just don't exist. And when this happens, there's a lot of different links in the food webs that are actually broken. And while in the modern day, yes, we've lost a lot of animal life that's breaking even more of those links, these researchers actually looked back about 130,000 years and were able to find that, yeah, probably about half of these have broken since that time. And it's not just because of extinction. It's also because of things like range changes, where the animals don't live where they used to anymore. And this breaks some of those links, meaning that those other organisms have less organisms themselves to try and feed on. And this includes herbivores feeding on different types of plants, where if they don't live where one particular type of tree they would feed on is, then they can't try and capitalize on that if that would be a food source that they would have normally interacted with. And the same thing tracks for if predators are hunting prey, where if those two populations get separated, well, the predator's not going to hunt it anymore. This means that we need to actually do a lot more work trying to understand how important many of these food web links actually are, because as they continue to collapse and fail, it does threaten the long-term survivability of the overall ecosystem, because there's just not that broader sensibility that we would want. And going back just a little bit further, actually, in South America, we can actually look at some fossil animals that actually hunted ground sloths and a lot of other animals in South America. And that's many of the crocodilians that are actually still there. Some of these, though, aren't, and some of them could have potentially been the largest crocodilians ever. Normally, when we're thinking about large crocodilians, and especially in the fossil record, we think of things like Sarcosuchus coming from Africa or Deinosuchus coming from North America. Meanwhile, though, Purosaurus lived only about 5 million years ago and was rivaling both of those for size. Purosaurus was a member of the Caiman family, and these researchers looked at 352 different specimens of all 24 living crocodilian species and tried to come up with a better way of estimating its length. Because in general, Purosaurus is known basically just from parts of the skulls, because the skulls are pretty heavy and more likely to fossilize because of that. What these researchers found is that depending on whether or not you're using the head width or its length, you're going to end up with different numbers. So these may actually be the most accurate measurements for Purosaurus that we have yet. And what they found is actually pretty interesting, because it wasn't quite as much of a monster as many authors had set it out to be. Because many authors had said, oh yeah, this thing absolutely could reach 40 feet, or about 13 meters. Meanwhile, based on this new study, it seems like it was a lot closer to 8 to 9 meters. Now, this is still a lot bigger than any other modern crocodilians. Even the largest saltwater crocodilian on record is only about 6 meters long. So Purosaurus was still a lot larger than anything we have today. And it's unfortunate that the ecosystem in South America changed so much and they did go extinct, because it would be really cool to see something that massive even still today. But when a lot of the other fauna did die out, it probably did too. Because when you're that big, you do need sometimes to eat larger things. On the subject of crocodilians, they are archosaurs. And archosaurs are just one group of the reptiles, but it includes crocodilians and also the dinosaurs, and by extension, technically the birds as well. And this study was looking at how their eye changed in relation to bite strength and bite efficiency. And this is actually really exciting, because when we think about especially dinosaurs, we can look at something like Coelophysis, which was a relatively small theropod which had a very circular orbit, so you can see where the eye would fit in really nicely into that circle. Meanwhile, when you look at larger theropods like Tyrannosaurus rex, but also Scorpiovenator, you can see that orbit shape changed a lot, and the eye didn't scale entirely the same way that it would with smaller dinosaurs like Coelophysis. And so why is that the case? It seems like it has a lot to do with bite force, and narrowing that eye socket actually does help make the bite more efficient, as is shown in this model using Tyrannosaurus rex. And this tracks in a lot of different archosaurs, especially the more carnivorous ones, where as they got larger, the benefit of having a larger eye became less and less, and it became more important to have a more efficient bite. So it seems like this overall eye change shape was actually really important for letting the archosaurs become the most massive predators that have ever walked the planet. One set of organisms, though, that also developed large heads didn't actually change their eye shape that much, and that's the ceratopsians, of which there's a new one coming from New Mexico. This one has been named Bisticeratops, and it's actually kind of unfortunate the way it's preserved, because it's missing one of the really important bones for identifying and helping to tell apart different ceratopsians, and that's the parieto-squamosal bone, which is part of the frill. This is really important for especially understanding the overall evolution of ceratopsians through time in North America. And since it doesn't have that, it's really hard to use it as a defining feature for how it might be related to other ones. That said, there are still features, like some parts of the front part of the skull, especially around the teeth and the snout, that do help distinguish it as a distinct species. It just means also that when we put it into a phylogenetic matrix, that matrix may not be as accurate as it could be. Still though, Bisticeratops in this analysis does show up to be more closely related to some of the more northern North American ceratopsians, as opposed to some of the ones that come more famously from the southern part of North America, with things like Caimaninae being just one of these animals from southern Arizona. During this part of the Cretaceous, there was a large inland sea that would have covered a lot of the continent, but it does mean that it didn't necessarily totally isolate the different parts from north to south, because there were still some connections for some of the northern ceratopsians to migrate southwards, and likely some of the southern ceratopsians to migrate northwards. So it's a really complicated environment where the ceratopsians would have been pretty much everywhere. At least as far as we can tell, they were pretty widespread in North America, meaning they would have been an important factor both as things eating the plants, but also when they were getting eaten. And the thing is, most ceratopsians weren't actually that big like Bisticeratops. Instead, most of them were small like Psittacosaurus, and there's one famous Psittacosaurus that was preserved incredibly well, like skin and cloaca and belly button and some feather-like structures that people still argue about if they're feathers or not. I think they are. But this paper actually looks at the overall collection of what has been found on that specific specimen of Psittacosaurus. And it's a lot of summary of things that we've found in other papers, like, hey, we have a cloaca, which is where it pooped and peed and did anything else it needed to from. And hey, it had a belly button, or at least an umbilical scar for where the animal would have been attached to the side of the egg and the yolk sac. The more important part, though, is that these researchers actually started to apply what they had learned beforehand and start putting it more broadly into context of overall dinosaurs. This is because a lot of the scales vary in size, and so by comparing that with other ceratopsians, we can try and understand scale evolution in ceratopsians. But then also by comparing it to other animals that also have scales preserved, we can try and understand how scales evolved in dinosaurs as a whole. So it's starting to put it into that broader context that's really useful for paleontology. There are some other fossil dinosaurs that also preserve some parts of organic material, and this usually isn't completely original, but sometimes it can be, especially with some things like collagen, which are just some fairly simple but relatively sturdy protein strands. The researchers in this case were actually looking at one animal that has this kind of preservation. It's a Brachylophosaurus coming from North America, and the researchers, again, weren't studying specifically the proteins, but instead were actually trying to better understand how the proteins got preserved in a process called taphonomy. Taphonomy is just everything that happens to the organism after it dies. In order to understand what happened to this Brachylophosaurus, the authors split it into large-scale and small-scale events, or micro-events and macro-events, with macro being large and micro being small. What they first found is that it would have died in the normal decay processes would have began, but eventually got transported by water. And that's a really important step because it would have been buried at least partially by mud and sand when this happened. Now, water still would have been able to flow through, so then later in the taphonomic stages, it would have had that water actually get into the bone. And that's when you start getting a lot of the mineralization happening, where trace elements actually start replacing some of the parts of the bone. That said, more sand and mud would have still been deposited on top, and would have pressed down the sand and mud that was directly on top of the fossil. This would have essentially locked the water that was inside those bones. It wouldn't have had any kind of escape route to flow outwards. Because of the water locked inside, the continued mineralization of trace elements into the bone would have continued. And it also means that some of these things could move around a little easier in that water as they dissolved into it essentially, but it also means that there wasn't a lot of other changes happening, meaning that some of these proteins were actually stabilized. And then as the fossil starts to get eroded towards the surface, the water can escapes, but those changes in the protein still hadn't been made yet, meaning that when researchers actually uncovered these fossils, there were still some of those proteins present in the bone. And staying on the subject of soft tissue is this paper, which when you see the title, you might go, wow, soft tissue in a sauropod, that's really exciting. But again, this is just the kind of protein and collagen preservation, nothing that actually tells us what the actual appearance of a sauropod would have been. But still, it is exciting, and these researchers were doing the same thing, trying to understand how it got preserved. And what they did is they actually mostly looked at the sediment surrounding the fossil instead of the fossil itself. What was the depositional condition that this animal died in that actually caused the preservation to happen? And what they found is that it would have been in a fluvial system, so there would have been a stream flowing over the animal. But then again, of course, and this is a really important part potentially because it tracks with some other fossils with this, it had a really low amount of REEs, or rare earth elements. A lot of times these are very heavy metals like neodymium, and so actually not having these is As much as they're rare earth elements, they actually are relatively common. The reason they're considered rare is because it's just not financially viable to dig them up that regularly. So having something that actually is depleted in rare earth elements is pretty unique. It's not something we would normally expect to find. But since a lot of other fossils with this kind of preservation have the same sort of environment, maybe that is the case, that you need fewer of these heavy metals that are going to actually go in and replace some of these different chemical bonds that would have been present in these proteins. And all of this taphonomy brings us to another taphonomy paper, this time looking at preservation of fish, because sometimes, like in Lagerstadt, which is a fancy word for just saying this has really good preservation, you have really, really great fossils, like this moonfish, where you can still see the pattern it would have had in life. But how do you get that? Well, researchers know that fish decay, but they haven't really actually watched that in a scientific manner, at least up until now, where they took some sea bass and actually put them down and just watched how the animal broke apart. And it was a long process over a few months, but they have an image that really shows all of the steps in pretty good detail. And this actually includes the different days that some events happen. So on the first day, it's freshly dead, which makes sense. But then first the heart and liver start to decay and are entirely gone by day 4. And this is before any type of mineralization and serious chemical changes can happen other than that decay. This means that other organs that actually stay in the body longer when the animal's decaying are more likely to get fossilized. And that's because oftentimes these are phosphoratized, meaning phosphorus replaces the structures that are present in the tissues. And phosphorus is actually kind of common in the bodies. It's one of the things that makes up DNA. Additionally, in order to get those chemical changes, you need to be at a fairly particular pH. But the thing is, as the body decays, it actually eventually reaches that pH, meaning that's not a super specific factor that's needed. It just so happens that as it reaches that pH, it's right about when the stomach is starting to decay. And that means you can actually get some of the body's phosphorus to phosphatize the stomach and potentially even stomach contents. This is actually what we see in that moonfish that I showed earlier. You can see parts of the stomach, and there's some shrimp and other small animals that are inside of its stomach. So this is actually really cool for understanding how fossilization of some of these really, really well-preserved fossils may have actually happened, and how the decay of the organism may actually enable us to understand when exactly it was fossilized in the decay process because of that pH scale, but also where a lot of the materials that are actually fossilizing the animal from, because it's the phosphorus in the body that actually lets us get these fossils. And now we're moving into papers that I can't transition to as easily, and this first one is looking at an impact structure off the coast of West Africa, specifically on the Guinea Plateau. And what they did is they mapped out the bottom of the seafloor on this plateau, and they noticed that where the Cretaceous ends, there is a dip there, and it's relatively small, only about 8 kilometers wide. Now that's a lot different than things like the Chicxulub crater, which is more or less credited for killing off the non-avian dinosaurs, which is about 180 kilometers wide. However, it could potentially still be part of the same impact, with potentially a meteor or a meteorite coming into the atmosphere, breaking apart, and a small piece of it hitting off the coast of West Africa. And now for a pretty broad change of topics, we're actually going to go all the way back to the Cambrian for 2 different papers. The first looks at an animal that was thought to be one of the first deuterostomes. And to understand what a deuterostome is, you need to understand how embryos develop, because very, very small embryonic animals that don't have vertebrae develop differently than those that do in some of their relatives. Deuterostomes include the vertebrates and the echinoderms pretty much. So it's just those 2 groups that develop by developing their anus first and then their mouth separately when they're actually starting to make the inside of their body cavity. Essentially, it starts from one side and then the other side meets up with it. The other main group of animals is proterostomes, which do the opposite. They develop their mouth and then their anus second. So what does this mean? Well, there was one fossil, Saccharoritis, that was thought to have been one of the first deuterostomes. And that's really odd because, just look at it. It is a very bizarre animal that lived during the Cambrian. And from what researchers had thought they had understood, the single large opening was thought to have been the mouth, and it lost the anus, which then also means it would have needed to excrete through the mouth as well. So it's something that's really not thought about even in modern day deuterostomes, where even things like echinoderms, so things like sea urchins, we don't really think about as having an anus, but when we look at their fossils, They do. It's the little hole on the side, and then the hole in the middle is their mouth. So it's a strategy that doesn't exist in the modern day, and that caused some researchers to look at this fossil in a little bit better detail. And they found a couple of other things that don't really line up with the deuterostome idea. One of the most important things that we do find in modern day deuterostomes is water pumping systems. For us, it's our cardiovascular system, where the heart pumps blood, which is like a water, through our body. Meanwhile, echinoderms do have a specific water pumping system. It's how the tube feet work on things like sea stars. So the fact that Psittacosaurus didn't have anything like this suggested it may not have been. And in fact, the researchers found it not to be a deuterostome at all, instead being closer to things like the nematodes and the arthropods. Those are specifically ecdysozoans, and ecdysis just means it's shedding its skin. So if you think about some spiders where they shed their skins, it's the exact same thing, only not necessarily as quite of complex of a carapace as a spider has. Now, Psittacosaurus was very small. For example, the scale bar in this reconstruction is only 500 micrometers in length, so these things were absolutely tiny, and probably lived very close to the sea floor. That also means that we don't exactly have an exact direct comparison for how this animal would have been living. But it does help us to understand that at least some of these groups, like ecdysozoans, were already diversifying pretty well by the time Psittacosaurus lived during the Cambrian. Now, going back to the Cambrian, there's something called small shelly fossils, or sometimes small carbonaceous fossils, like in this paper. What these are just assemblages of very, very small fossils that we can tell probably came from something living, but we don't exactly know what it was. And that's because a lot of times these are very broken up, and so we can tell it's the pieces of something that had a shell, but we really can't tell more than that. Sometimes, though, we get really great fossils from it, including these fossils coming from Canada. These fossils come from the earliest part of the Cambrian, and they're so well preserved that we actually can tell that some of them were at least arthropods, meaning things with shells and bony joints. So think of crustaceans and insects and some of their relatives. This is actually really helpful because it helps us to understand exactly when this radiation may have started. Many of these fossils are really partial, but at least some of them preserve claws. And there's actually a whole huge list of different types of fossils that they did find in here, and they don't necessarily all line up, meaning that, again, this group was already pretty diverse, and it helps to actually lend a lot of credence to the idea that arthropods were already diversifying before we find them more commonly in things like the Middle Cambrian, where the trilobites start first really showing up in large numbers. And now moving on to other papers I talked about the Lystrosaurus mummy. Lystrosaurus was an animal that lived through the Permian-Triassic extinction on land, and this was the most extensive extinction that the planet has ever seen. And some of these fossils were preserved as mummies, meaning that there was some skin preserved. Hopefully with that we'll be able to get a better understanding of what it would have looked like in the future, because this paper mainly focused on the different mechanisms in the geologic record that allowed the skin to actually be preserved. There's also a paper looking at Mosasaurid, or the American cheetah, and some of the collagen that's preserved in its bones in Natural Trap Cave in Wyoming. There's also some of its potential prey items there, most notably pronghorn. And by comparing the collagen, we can try and identify what the different isotopic signatures of the different organisms found in this trap cave would have actually been. And it does suggest that Mosasaurid did feed on pronghorn at least a decent amount of the time, however, not enough to say that they were specialized on only pronghorn. So it's really hard to say that the pronghorn, the fastest animal alive in North America today, was actually pressured by the American cheetah to run as fast as it is. There was also a new thyreophoran dinosaur coming from South America, named Jacopil kainukura. It's actually really unique. It seems like it was a very early diverging thyreophoran, with most thyreophorans being things like the ankylosaurs and the stegosaurs. Meanwhile, it seems to have diverged from those two groups before those two groups diverged from one another, meaning that there's potentially a very long hidden lineage of thyreophorans that existed in South America for millions of years. Additionally, it may also just not be a thyreophoran. The fossil was kind of incomplete, and some researchers have suggested that maybe it was actually a ceratopsian. Hopefully we'll get some better fossils of this in the future so we can better understand what exactly it was. Hey everyone, thanks for watching. It's been great getting some support for the channel as we've been continuing to get stuff out there. I will be at Geological Society of America, so if you see me there, say hi, or don't. I'm not the boss of you. Don't forget, we do have a Patreon where you can help vote on some of the things for the channel, and a Discord where hopefully in the near future, from when I'm recording this, we're going to be trying to do a watch party for some of the paleo docs that are out there. Yeah, paleontology is neat. I don't know what else to say. Be safe, take care, and don't go extinct.